everyone to the Seas colloquium. We are very delighted to have Shima Abadi speaking to us today. Shima received her Bachelor's of Science degree in Mechanical Engineering from the University of Tehran in Iran in 2008. Her master's degree is in Mechanical Engineering from the University of Michigan, and then she has an additional degree in Applied Mathematics. Her PhD in Mechanical Engineering was finished from the University of Michigan in 2003. From there, she became a postdoctoral researcher at Lamont Doherty, just here very close to us, and then moved to the School of Oceanography at the University of Washington from 2013 to 2015 as a visiting scientist. She's currently an assistant professor in engineering and mathematics, and also a professor of electrical and computer engineering at the University of Washington. Her research primarily focuses on acoustic signal processing in ocean sciences. She's worked on a broad range of topics such as blind deconvolution, sound source localization, the direction of arrival estimation, acoustic imaging, and bioacoustics. Dr. Abadi received 2 Best Paper Awards from the Acoustic Society of America in 2009 and 2013, and she is currently working on mitigating seismic airgun noise, analyzing ocean ambient noise, and developing graph signal processing algorithms for analyzing data collected by large, dynamic, and irregular water networks. And with that, I would like to welcome Dr. Abadi and give the floor to her.
Thank you so much, Dax. I really appreciate for your kind introduction. Thank you so much for inviting me. It's very nice to be here. So let me share my screen first. Okay. So today I want to talk about ocean ambient noise, and in particular, the noise that we get from wind and rain in the ocean. But before starting my talk, I would like to thank my students who all the figures, plots, and results that you see in this presentation are their work, Felix, John, and Matthew. I also like to acknowledge my sponsor, Office of Naval Research, and in particular TFO, Task Force Ocean Program in ONR for sponsoring. And I also like to thank OOI Network for providing the data that I use in this project. Okay, so I want to introduce you to Ocean Soundscape, but before going to the ocean, let's imagine that you go to someone's house that you don't know, right? You don't know the environment, you don't know what time of the day it is, you don't know that person. But just by listening, you can hear a lot of things, and you can find out a lot about the environment and about the host. For example, if you hear a dog barking, you know that person has a dog. Our ears, both of them, can do the directionality, so you can find the direction that the sound is coming from, so you know where the dog is. If you hear like cooking, if you hear the sound of cooking, you know that something is going to be prepared for you soon, right? So you can predict what is going to happen in the future. You may hear fan that is on, so it probably tells you that it's summertime. You may hear, I don't know, a kid crying, so you know that person has a kid, and by just listening to the sound of that crying, you can maybe guess how old that kid is. So just by listening, just passively listening to the environment, you can hear a lot of sounds, and you can learn a lot about the environment. The other example is when you are in a forest. You know, you can hear different animals, you can hear rain, you can hear wind. These are all the things that we hear, and we learn a lot of things about the environment. And now we want to go to the ocean. So what if we are in the middle of the ocean, down deep in water, and what can we learn about the environment if we just passively listen to the recordings? This is what we call ocean soundscape. As you can see in this image, I'm showing you a couple of sources that contribute to the ocean soundscape. For example, we may have marine mammals that are vocalizing. You can hear them. You may have earthquakes. You can hear earthquakes in the signal. You can hear ship noise. Sometimes they're really loud. You can hear storm, rain, wind, breaking waves, all those activities that happen on the surface of the ocean. So the goal of my project in general is characterizing ocean ambient noise and see if there is any pattern and be able to predict the future level of the ambient noise. For example, can we learn about marine mammal calls? We know that those vocalizations a lot of times are seasonal, so that we can get the seasonal pattern. Also, a storm might be seasonal. We may get more storms during winter than during summer. So what can we do with this data? And it's going to be a big data, right? We're recording 24/7. What can we do with that? How to analyze that? How to characterize different sounds? How to distinguish them? And how to predict a model for future prediction. This is what I want to do. But for this talk, I will focus on only wind noise and rain noise and how we characterize those noises in the ambient noise. Okay, so the data that I'm going to use is collected by OOI project. It's the Ocean Observatory Initiatives. I'm sure a lot of you are familiar with this project. They have multiple arrays around the globe, and there are multiple instruments in each array, recording data in 24/7 for multiple years. What I will do is I will focus on these two arrays because we have hydrophones in these two arrays. Both of them are in a Northeast Pacific Ocean, regional cabled array and coastal endurance arrays. In these two arrays, overall, we have 11 hydrophones. 5 of them are broadband, and by broadband I mean we can record signal that we can capture signal with a very broad frequency range. The sampling rate is 64 kilohertz, and rule of thumb is that we can listen to the signal up to half of the sampling rate, so that we can listen to a signal up to 32 kilohertz. We have 6 low frequency hydrophones, so we can only focus on low frequency signals. And the sampling rate is 200 hertz, which means we can listen to a sound up to 100 hertz. And these are the lists of the instruments. We have a lot of them here close to some of them close to the shore and on the slope. And some of them are very close to the axial seamount, as we will see in a minute. Accessing to the data might be challenging for OOI because hydrophone data is big. It's not easy to get that data. The data right now is available only in raw format, in mini-seed format. So my students have developed a Python toolbox for accessing and analyzing these data set. It's called OOI Pi, and it has been released. So if you want to just play with that, you can go to the GitHub. There are notebooks, examples that you can just follow and get the hydrophone data and analyze it on your own. Just roughly showing the location of the hydrophones relative to the other sounds in the ocean. Let's just start with shipping routes. This image shows the shipping density around the hydrophones. So I'm showing the rough location of hydrophones by black circles. Some of them are here, some of them are here, and you can see that they are very close to main shipping routes. So we probably get a lot of ship noise in our data. Location of the hydrophones relative to earthquakes that we get is also shown here. So you see the number of earthquakes during past 5 years, and some hydrophones, I think, and only low frequency hydrophones are listed here. And also we get a volcano. We have a volcano very close to our hydrophones, axial seamount, so we may hear eruptions in our data too. I'm not a seismologist. I'm sure there are people who know more about earthquakes than me in this room. So I just wanted to show the relative location of hydrophones to the most of the earthquakes that we see. So if we see an earthquake signal, we know what it is. Okay, so I want to show you some examples. Usually in acoustics, when we talk about signal, when we want to visualize signal, we plot the spectrograms. Spectrograms are figures that show frequency on y-axis, time on x-axis, and color represent the loudness, basically. So red means very loud, and blue means quiet. What you see here is, it's very nice. Why do we check a spectrogram? Because, well, we can see the temporal signal, the time series, and also the spectrum at the same time, right? If you just listen to the time series, it's very hard to know the frequency of the signal, right? But we can look at the spectrogram and see both at the same time. So, for example, what do we see in this figure? Let's start with this little red area around 20 hertz. These are fin whale calls, the usual 20 hertz calls that we get in the hydrophone data. So you can see them here, right around 20 hertz, right? What else do we see? Maybe these strong broadband signals, these are local shipping noises. You see that these are broadband because it covers a very broad frequency range, and it's impulsive, right? It's impulsive relative to the time axis that I have, but if you zoom in, it may take a couple of hours until the ship gets close to the hydrophone and gets further from the hydrophone. We can see that signal. We also see macrosystem noise in our data, and if you have other noises, you will see that in this spectrogram, and you can find them, you can separate them from the other sources, and you can analyze them. So what we want to do in this talk is we want to focus on wind and rain noise. So let's see the spectrogram of wind and rain noise. What you see here on left-hand side is a sample wind spectrogram, and on right-hand side, you see a sample rain spectrogram. You can see the differences just by looking at the spectrograms. The frequency range is the same, the time axis range is the same, but what you can see here is that if you have wind, it's kind of like random noise, like the whole spectrum is has a higher level, right? It's kind of like, if you listen to that, we will listen to that in a second, it's kind of like noise. But in rain, we get some frequencies higher than the other frequencies, as you can see here. Sometimes the range is different depending on the rain rate. That range changes. And then you can find the start time of the raining event, the end time of the raining event, how often it happens, and all the other information that we will discuss in this talk. So let's hear with this wind noise. So it's kind of like a uniform distribution of noise and frequency, a little bit higher a spectrum in lower frequency and a little bit lower in a higher frequency. But let's listen to the rain signal. Okay, just by listening to the signal, you probably were able to hear the differences, right? But how can we quantify that differences, and how can we model rain noise? That's what we want to cover. Let's look at the monthly average of spectrograms first. So this one shows a month of hydrophone data in axial base location during February 2019, and this one shows the same data at the same location in October 2019. You can see the differences, right? You can see some rain happening here, and it's less during October. So it kind of makes sense. We should expect to see more rain in February compared to October. You can also see wind noise in both months. Sometimes it's higher and sometimes it's lower depending on the time, right? So this is just an example of what happens in a long time. Basically, you can look at the whole year, you can look at whole 5 years and all those things. What we are doing is we want to use the whole data set that we have starting 2015 up to 2021 and analyze that data set. we will use two types of data. We will use the acoustic data first, which is measured by the OI broadband hydrophones. You see an image of the broadband hydrophones here. The data that we use, the hydrophones that we use, sit on the seafloor like this. We need to know the rain rate and wind speed information. So for that, we use the surface buoy deployed very close to the hydrophones that we are using. And you can see that some of them are kind of like home to some sea lions that are relaxing here. So we're going to use these two types of data. We want to combine them and analyze what we get in terms of noise. Going back to the hydrophone map, this was the hydrophone map of all the 11 hydrophones. We will show data for these two hydrophones for this talk. So we want to focus on Oregon Shelf hydrophone and Oregon Offshore hydrophone. From now on, we will call them shallow side and deep side. Shallow side is the Oregon Shelf, deep side is the Oregon Offshore location. Shallow side, the depth of water is 80 meters. A hydrophone sits on the seafloor, so it's at about 81 meter depth. In deep water, we have a water depth is 581 meter, and hydrophone sits on the ocean floor. What you see here is the location of the hydrophone, as I show by H, relative to the location of the surface buoy that I show by B, in shallow side and in deep side. And you can see that there is a displacement. The surface buoy is not exactly on top of the hydrophone. It matters because once we see the data, we will see a delay between what we measure in terms of the rain rate and what we see in the spectrogram in terms of noise. So we should find that delay and fix that delay. And that delay, the portion of reason for that having that delay is because we have a displacement between the surface buoy and the hydrophone. In this figure, I show an example of a speed of sound profile at both locations, deep hydrophone here, shallow hydrophone here, in 2 months. So I took August 2018 and February 2016, just as an example, 1 month during summer and 1 month during winter. Speed of sound profile is very important for ocean acoustics because, as you can see in this image, it's not a constant number. In air, the speed of sound is constant. Actually, you can assume it's constant because the changes are very small. But in the ocean, speed of sound is not constant. As you can see, we have depth on x-axis, and we show the value of a speed of sound on x-axis. So you see a big difference, especially during summertime. There's a big difference close to the surface. Well, I can tell you that the speed of sound is a function of temperature, salinity, and pressure, which is basically depth. So just by knowing that, you can guess that we get a difference in summertime because water close to the surface is warmer than water deeper into the ocean. So we get a difference in the speed of sound due to the difference in the temperature. And as we go deep, the speed of sound increases a little bit, and that's because when we go deeper, we get higher pressure. And if you think about the pressure is related to how much water we have above us, we get more water, so we get more pressure, and hence we get higher speed of sound. I'm sorry, lower speed of sound. They have reverse relationship. Anyway, so why do we need to know speed of sound? Because we want to understand the propagation. We need to simulate the propagation of noise on the surface and what we receive on the seafloor, because we want to know what the effective surface listening area is. Now you have a hydrophone, it has a listening area. It can listen to the signals that happens in a circle around the hydrophone. What is the radius of that circle? What I show here is the effective listening area for deep hydrophone on left-hand side and for the shallow hydrophone on right-hand side. You see the listening radius on x-axis and the fraction of energy received on y-axis. It has been normalized. What we want to know, let's set a threshold for the fraction of energy, and let's say 90% is enough for now. Okay, at what radius we get to 90% of the energy? And I show two colors. Blue is during winter time, red is during summertime, and I show three different frequencies here. We can discuss this figure a lot, but what you need to know just for this talk is the differences between deep water and shallow water in general. In general, the effective listening area in deep water is much more than the effective listening area in shallow water. Rule of thumb is that if you have a hydrophone at depth D, the radius of effective listening area is 3 times D. So that makes sense. In deep hydrophone, depth of the hydrophone is 580 meter. In shallow hydrophone, the depth is 80 meter. Because the deep hydrophone is deeper, the effective listening area is larger. Okay? So because of this phenomena that I just explained, right, that the effective listening area, and because we have displacement between the hydrophone and surface buoy, we get a lag between what we measure in the data and what we have in the spectrogram. And I will explain that in a second. Before that, just let's take a look at the sample wind speed data that we get. So it shows wind speed data measuring during about 20 minutes of data. What you see is that this data is pretty noisy. It goes up and down a lot. We want to smooth that figure, so we just use a moving average filter to get the smooth wind speed data. And we will do that for rain data too. This one shows rain rate as a function of time, and gray dots show the measurement at each time, and you see that it's noisy. It goes up and down a lot. We apply smoothing averaging filter to get the black line. This is the smooth version, and then we set a threshold. The threshold here is 2 millimeter per hour, and then if the rain rate is above that threshold, we call that a rain event, and we capture the rain data and we capture the noise data, and we will find a correlation between them. But let's go back to the lag that I just explained. What you see in this figure is the spectrogram during one of the rain events. You see we have one rain event here, one rain event here. This data right below that shows the rain rate that was measured at the surface buoy, and you see that there is a lag. The peak of the spectrum is here, but the peak of rain rate is here. Same thing here, the rain event happens at this time, but a little bit after that, we get a peak in the rain data. So in order to fix that lag, we will compute the power of the energy. Basically, we take the average of all the frequency that you see in this spectrogram, and we show that by this black line here, the power line, and the lag is clear, right? The lag is clear. And then we interpolate rain data to get the same number of samples that we have in the noise data. Then we calculate the correlation between these two functions, and the peak of the correlation, actually the time of the peak, gives us the time of the lag. So in this case, we have 204-second delay, and we will fix that delay in the rain rate data. We shift it back so they align, and then we save the data for analysis. Okay, one more step before showing the result is that what's the metric for noise? What metric we want to use in order to do the analysis? The metric that is common in acoustics is called spectral level, which shows on y-axis shows how loud the signal is, and on x-axis shows the frequency. So we know at each frequency how loud the signal is. In order to do that, Welch method is a common approach to calculate the spectral level. But what do we do in this approach? We divide the signal into different segments, small segments. I show 3 segments here. And we calculate the spectral level in each segment. It's called periodogram. And then we take the average of all these periodograms, and we calculate the average spectral level. So we see a spectral level on y-axis, which shows how loud the signal is, and we see frequency on x-axis. What do we see here? Well, we have high frequency energy, and then, we have high energy at low frequency, and then energy decreases as we go to higher frequency, but we get these peaks here. Well, these peaks, if you look at the spectrogram, are due to these impulsive signals that we have in the data. These impulsive signals are due to some other instruments that are co-located with the hydrophone, like ADCP pings, for example. That we don't want to analyze those pings. We want to analyze what's behind it. What is noises? What noises the wind is causing, or what noise the rain is causing. So if we keep this spectrum, spectral level, we don't see what the level is, right? We just see the level due to the pings. So how we can remove those pings? We analyze or we expanded the Welch method to a Welch percentile estimator. That the only difference is that instead of taking the average of all these periodograms, we take some quantile of that. Let's say we take the median of that. If we take the median of that, those peaks are gone, as you see here, because they don't happen very frequently in the data. They happen less than 50% of the time. So by taking the median, we can remove them. The only peaks that you see in the blue line is due to these tones that we have, and it's consistent in the whole period. And those are also instrumental noise, but we cannot remove them. Well, we can remove them, but that's not what we want to do here. So that's the technique that we use to get the spectral level. Now let's take a look at the results. We're going to start with wind noise result. Over the 5-6 years of data, after cleaning the data and pre-processing, we get about 11,400 hours of data. And then we combine the data, we take the average of all data points that we have to get these two figures. We have a spectral level on y-axis, frequency on x-axis, shallow location on left-hand side, deep location on right-hand side. Different color means different wind speed category. So we have a smaller spectral level at lower wind speed, and as wind speed increases, we get higher spectral level. Now we want to model this noise, right? We want to have an equation. So if we know the wind speed, we can calculate the spectral level. What's the best model? We think the best one or the easiest one is having different models for different frequency range. If we have a linear model between 0.2 kilohertz and 3 kilohertz, as you see here, and then another model between 3 kilohertz up to 25 kilohertz, as you see here, and we can fit linear regression, which is an easy model, and we can use that. We can talk about different behaviors that we see in these figures, but what I just want to mention right now are two things. One thing is that look at the slope of high frequency spectral level. They're usually kind of like separate. The spectral levels are separate. The slope is the same for different wind categories, except for the high wind category. This gray line is for wind speed greater than 14 meters per second, which means the spectral level drops very fast at higher frequencies if we have high wind speed. Well, if we think about that, why we get different behavior at high wind speed compared to the low wind speed? Well, if we have high wind speed, we get more bubbles on the surface, right? The ocean is noisy, and then we get a lot of waves, and a lot of breaking waves generate bubbles. And so we get a layer of bubble on the surface, which is kind of like masking effect. We get the masking effect due to those bubbles. So noise at higher frequencies cannot propagate to the deeper part of the ocean, and we don't get it in the hydrophone, so it drops really fast. But we don't see that in low frequencies, and also we don't see that in low wind speeds. The other thing I wanted to mention is this little peak that we see in deep location, not much in the shallow location, maybe a little bit in the low wind speed. That peak is not due to wind noise, it's due to distant shipping noise or distant storms. And by this, I mean not above the hydrophone, very far from the hydrophone. That because of the bathymetry, we get it in the deep location, but because of the slope of the continental slope, we don't get that in the shallow location. So ship noise from distant ships or storms cannot propagate into the shallow location much, but in the deep location, we get that contribution. It is at low frequency because only low frequency can propagate long distances. Higher frequency dissipates fast, so we don't get that. It's not like the ship noise has only low frequency. It has a broad bandwidth, but higher frequencies dissipate. We don't see them here, but low frequency, we get that. Okay, see how much time I have. Okay, let's compare what we found in terms of wind data with what has been published before. So you see our data with blue and red, and different people have reported different spectral levels. And one thing I wanted to mention is that you probably read Wen's paper. Some of you you probably read that. This is a very kind of like a baseline for ocean ambient noise. Wen's has analyzed a lot of data sets. So you see that Wen's data is below what we have here. It could be for two reasons. Well, Wen's data is for 1962, like many, many years ago. Maybe ocean is noisier these days. That's just maybe. We need to analyze it more. The other reason could be that Wen's recorded data in a combination of locations in open ocean and also in coastal environment, but our data is on the continental shelf. So if you look at the other two data that match with our data more, and go back to the location of those recordings, we'll see that those are recorded at a similar environment. So one conclusion that we can get from this figure is that wind noise is site dependent. It depends on which location we are looking at, the noise level will be different. So let me skip this slide in order to get to the rain noise, and if we have time, I will come back to that slide. Now let's focus on rain noise. We have, again, after cleaning data and pre-processing, we have 280 hours of rain noise data. And then we do the analysis, combine the data, we take the average to get the spectral level as you saw for wind, this time for rain. What I'm showing here is a spectral level on y-axis, frequency on x-axis, deep location on left side, shallow location on right side. Different color means different wind speeds, and I show two different categories of rain rate, 2 to 5 millimeter per hour and 10 to 20 millimeter per hour. Again, we want to model this noise. So we found out that if we have two different frequency ranges, it's best to have a linear regression model in these two frequency ranges, as you see with dashed lines. But we cannot have a linear model at higher frequencies. At higher frequencies, we have a nonlinear model for that, which is similar to a low pass but high pass filter, kind of like it looks like that. But you see the behavior is different. You know, this side is a deep location, this side is shallow location, and you see that for different wind speed, for different rain rate. So you see that the behavior is different. And again, so this is only at high frequencies, right? If we take the average, one thing I wanted to mention is that although we are focusing on rain noise and we expect that the spectral level should be a function of rain rate, right? But we found out that the spectral level is not only a function of rain rate, it's also a function of wind speed. So if we have same rain rates for two different events, and in one event you have higher wind, spectral level increases for that, which kind of like, it makes sense, right? But if we take the average of all those noises and in all those wind speeds, this is what we get, only a function of rain rate. So you see different rain rates here. And people have published results before that are a little bit below what we have. And again, it's because of the different locations. These results are in open ocean, were recorded open ocean, where our result is on the continental shelf. So it's the environment impacts the ocean noise level a lot. What is the frequency range of the rain noise? Is it a broadband signal? Are all the frequencies are contributing to the noise similarly, or there is a region or there is a bandwidth that contributes to the rain noise more than the other frequencies? In order to find that, we calculate the correlation between the spectral level and rain rate, and also the correlation between the spectral level and rain rate. So you see the correlation between the spectral level and wind speed here for different locations, and between the spectral level and rain rate here for different locations. What do we see here? Well, let's focus on deep location. For example, we see higher correlation between about 100, 200 hertz and up to 10 kilohertz, and then the correlation drops. So noise is not correlated with wind speed during rain events at high frequency or at low frequency. What about correlation between rain rate? The value of correlation in general is lower than wind, so wind speed has higher impact. But we get a peak at 13 kilohertz. So at 13 kilohertz, the rain matters a lot, the rain rate matters a lot, but wind speed does not. So that's a perfect frequency in order to do the analysis if we only want to have one dependent variable and not dealing with two dependent variables. And that's what I show here. So I just picked the deep hydrophone and I show a spectral level versus wind speed and rain rate. So wind speed on left side, rain rate on right hand side. The first row shows at 5 kilohertz and the second row shows what we get at 13 kilohertz. So you see the dependency of a spectral level with wind speed here and also with rain rate at 5 kilohertz. But at 13 kilohertz, it's almost independent from wind speed. It doesn't matter which wind speed we have, the spectral level stays almost the same. But it's a bigger function of the rain rate. So this frequency is a perfect frequency for if you want to develop a prediction model, and that's what we are doing right now. If we want to know, if we want to only have one variable and predict what the spectral level in the future will be. So summary so far, I showed a new technique for getting the spectral level when we have outliers like ADCP pings. I also showed you some results for wind noise, showed that we have different frequency range and different model for different frequency range. And then for rain data too, I showed different frequency range and different models. I talked about the frequency that we get noise independent from wind speed and only depends on rain rate. I want to stop right here, see if you have any question. Hopefully we still have some time. Yes, we have a few minutes. I would love to hear your questions. Thank you so much for your attention.
Thank you so much, Shima. I do absolutely believe we have a couple of questions. I know that the graduate students had several that were in the that they posted in response to your the Wentz article. I think since I think we've got lots of time. So Max, would you be so kind as to share the questions that you posted, or one of the questions that you posted?
Yeah, I guess I just that was really great. Thank you so much. I guess I just could you maybe comment on like the larger like applications, I guess, of this?
So there are two main applications. One is for remote sensing, that in the middle of the ocean we don't have access to nothing basically, and how can we, in the remote locations, how can we estimate rain rate and wind speed and get that data? If we deploy a hydrophone and if we have a good model for that location, we can do that. The second application is for Navy operation, because in Navy operation we need to know the background level, right? If the environment gets really windy or rainy, how can we operate the submarine? Because submarine only works with sound. All the functions that are done in submarines are by sound, navigation, detection, anything. So having higher level of background noise will have impact on that operation. We need to know the level of that and be able to know if it's due to the wind, it's due to the rain, or maybe there is an enemy close by or some other activities.
And if it's all right, Max, I'm going to channel one of your questions because I thought it was pretty interesting. Max asked about frequencies that marine mammals are sensitive to. And Shima, one of the things that you said while you were talking was that it was somehow cast doubt on whether or not there is a higher level of noise now than when Wentz collected his data. And I guess my question is that is there any doubt about that? Because there's so much more shipping noise that is all dominated in that 20 hertz kind of a space. My thought is that in the sound space where most marine mammals are operating, that there's a real inundation of sound in there. If you think about them from a prehistorical, pre-industrial context, the amount of new sound that's in their space, it would be just overwhelming.
Yeah, that's actually a great question. I want to refer you to a paper by Rex Andrew, who did a very nice long-term analysis of ocean noise. So what he found out is that before Rex Andrew, people predicted that we get a certain number of dB per decade increase in ocean noise, and he showed that that's true. From many years ago until about 1990, 2000, the ocean noise floor increases with the same amount that was predicted, but after that, it either stays the same or decreases at some locations. And that's mainly because the shipping density is saturated. We don't get more shipping in the ocean, shipping noise in the ocean. Exactly. And at some location, it decreases because of and maybe some areas are more sensitive to marine mammals, like in Puget Sound, for example. We have a lot of regulation in terms of protecting orcas. So we get some regulation that contribute to that decrease.
And has there been any improvement in the technology of ships to make them consider their noise as part of their design process?
There are many studies on that trying to make ship noises either quieter or at least change the frequency of the noise so it doesn't interact or disturb animals' behavior. But still, we get a lot of ship noise in the ocean. There are some research or activities in terms of developing a hybrid vessel or ship that is not just based on fuel, so it's much more quieter. But still, that's not true for all the ships that we have. A lot of them are really old and very noisy.
Wow.
But there are some regulations, like if they see an animal, especially endangered animals close by, they have to reduce, or if they are in the area that we know at that time of year we get a lot of marine mammals, they have to reduce the speed or reduce the activity. But that's also another whole area of research.
It's an area of debate, isn't it?
Yeah.
Right, because if you think about passing through a lane that has potential whale activity, the question becomes, with the length of those ships, whether or not the source of noise can get to them before the front of the ship would.
Exactly.
And whether or not slowing down actually helps them out or increases increases the time. If you had to run blindly across the street, would you run fast or would you run slow? Right. And I know that my instinct might be to run fast, but the current regulations have the ship slow down when it's kind of a blind circumstance.
Exactly. That's true.
Wow. All right. Do we have any other questions?
Yes, hi. My name is Melissa. I'm a undergraduate student. I have two quick questions. I hope it's not too long.
Sure.
I was wondering, I think for one of the graphs that you showed, I was just wondering about how the time was formatted. I know you had time and you had, I wasn't sure if it were dates or something. I was wondering if you can just quickly go back to one of the slides.
Let's do that. Was it in the rain data or
It was the
wind?
wind, I believe.
Wind data.
It was like towards the beginning, I believe.
Here. Let me know whenever you see that.
Yeah. Okay, that one, yeah. Yeah, because I see the time, but I'm just wondering, are those like that's 15-9-05, are those dates or something? Or
These are dates, yes, these are dates.
Oh, okay.
In 2015, and then time is between 8 and I believe this is 9, so 1 hour of data.
Oh, okay. I was just wondering,
Hour and minute.
it was formatted.
Yeah,
Okay.
does it make sense? So it's 8
Yeah.
hours, 0 minutes, and then up to 9 hours and 0 minutes. So this is 1 hour of data.
Okay. And then my second question is, it was for the when you use the power equation to adjust the lag. I think it was one of the slides that you showed. Yeah, it was this one. I just wanted to know, by using the power equation to adjust the data, do you think that it would skew the data a bit?
That's actually a great point. Maybe different frequencies are behaving differently. But let's see. I don't think that's a big difference. So by just taking the average, I mean, looking at the spectra, a spectrogram can tell us some. So you see that all the frequencies are kind of like happening at the same time. So if you have a peak in the rain rate, they all happen at the same time. So if you take the average at that particular time for all the frequencies, it gives us a good estimate of the power. So this is the kind of like an approximation, but it's a good approximation.
Okay, thank you.
Sure.
All right, do we have any other questions? Okay, so Tim, Dr. Eden has a question. Tim, if you want to, you can speak or put it in the chat.
Hi there, Dr. Abadi. Thank you. I'm a hydrologist. This is way outside of my area of expertise, but a very interesting talk. I was a little puzzled by the graph that you showed there with spectral level and rain rate, because if I understood right, the rain rate is the measured data on precipitation, but that appears later than the spectral peak. And I
talk about the lag, this one?
Yes.
Okay.
And I was a little puzzled by that. I would have expected the spectral data, the sound data to come a little bit later because of the distance and other considerations that you measured.
That's actually a great point. So we looked at the effect of maybe wind direction to this lag. Is it positive or negative due to the direction of the wind? But we didn't find any correlation. One thing we should maybe consider is that hydrophone can listen to a broader area. So if we have a rain in the listening area, we can detect it in the hydrophone, but in the surface buoy, the rain should be right at that location in order to measure that. So there is a difference between the location, and it depends. Like, let's go back to the map. Like here, for example, this is the hydrophone location from the top view, and this is the buoy location. And there is a surface area that hydrophone can listen. So if, let's say, rain is coming from this direction, hydrophone can pick it up sooner. And then when the rain gets to the surface buoy, we can measure it in that surface buoy. But you know,
okay, that makes sense.
It's kind of like
by that. Thank you. Very interesting talk, though.
Thank you.
All right, do we have any, I think we've got time for one more if someone would like to ask one. And otherwise, Dr. Abadi, Shima, thank you so much.
Thank you.
I am just delighted that you're able to come spend this time with us. I believe that that Stephen is going to do a quick introduction to next week's talk.
Oh, yes.
And then everybody, thank you so much for joining us, and we will see all of you next week.
And so, so just before you guys sign off, next Wednesday, my PhD student, Ben, is going to be giving a talk about basically the shoaling and the destruction of a beautiful seaway in the Caribbean called the Caribbean Seaway, which is now the Panama Isthmus. And he's basically, his data is really exciting. It's basically rewriting the history of the shoaling and constriction of that seaway during a time period between 12 and 10 million years ago. When ocean circulation changed, and that makes sense because if you close the seaway. And so I hope you guys will join us. He's put a lot of work into this, and I'll see you next week. Okay, take care. Bye-bye.
Shima, if you want to stick around for just a moment, we'll say goodbye.
Yeah.